will find that I will be posting rather exam 2 practice material. And that's because like we have exam 2 coming up. That's next week, next Thursday. And what I would like you to do is that I'll post some practice problems, and I'll also post like a back exam that's from fall 2020. Just go and like try to do the exam after like you've reviewed everything. Just go and do that in a timed environment. So once you do that, then only go and check the solutions. And I've seen that strategy works really well. And for those of you who struggle during the exam, who struggle with the time thing, that would definitely help them. So please go ahead and do that. And yeah, the format is going to be similar to what exam 1 was, like exactly 3 problems, maybe 2 to 3 problems, not more than that. And you'll have to submit it on Submittee within the 90 minutes time frame. So that's why I'm saying like try to practice in a timed environment. All right, so those are the announcements, exam practice, no homework this week. And yeah, well, that's it. If you have questions, you're free to ask anytime. And let's begin. So today's lecture is about sets. Let me check if I started to record. Yeah, I did. All right, so this is a new Python object type that we will be introducing, and we will look at it through the lens of a problem in which we'll be reading data from a file that's the Imdb file. And there is a zip folder that I posted under lecture notes on Submittee. There you'll find some files related to or like the txt files that we'll be working with today. So I've already posted that. All right, so let us begin. The problem that we're looking at is finding all persons in the Imdb file. As I said, I've posted that file already, but let's look at it, what exactly this is and why are we talking about it in the lecture on sets. All of that will become clear in a second. Okay, so this is the Imdb file. The original one is like huge in the sense that it has like around 250,000 entries. And we have like the smaller version of this Imdb where we are just like looking at movies from 2010 to 12. Again, this one also has like around 26,000 values. And what exactly does it have? And I think the lecture notes kind of explain that clearly because there's, as you can see, like there is a lot of spacing and like every line appears like in actually 2 lines, like at least the way we can visualize it, but it is 1 line, but because the editor is telling me that this is 1 line. So let's look at what every line has, right? So every line in that file has the name of the actor, the movie they've worked in, and when, like what year did the movie appear. Okay, so this is like the original one is imdb._data.txt. It's a huge file and it contains like these kind of observations or these lines, right? And the problem that we're looking at throughout this lecture is to find all persons named in the file. What does that mean? Like the person's name is the first field or the very first element on every line. And so we need to count these, but the question is asking us to count the number of different persons. All right, so what does that mean? Well, that means obviously this actor has worked in more than one movie, right? And so their name will appear multiple times. And we don't want this person's name to appear multiple times in my like final result. So my result is to go and capture the individuals whose name appears in the file, but it shouldn't be counted twice. So that's the problem that we are looking at. And that's it. Like, so that's the basic goal. And then we can like, based on once we have some kind of a data structure in which we have like these names, we can answer lots of questions like if this person exists or not, right? And like how many people were there and so on. So all of that will be fine. But what we have to do is first find all persons named in that file. All right. There is another variant of this imdb.txt that I've created, which I'm calling hanks.txt. That's because I've like pulled the names of actors whose last name is Hanks and put them in this file. And the question arises, why did I do that? Well, and you should be also doing the same when we start working with like bigger files with huge amount of data in them. I don't want like, obviously my code initially is going to error out, right? And I don't want that I should be running this entire like 260K some values again and again with that error in the code. So you should take out a small, for example, this hanks.txt has just like 40 lines. So take a small chunk of that file, put it somewhere, and then test your code with that. And then once you're okay, like once you're sure that it works fine with this, then go ahead and test with the larger file. So that should be the order of the way you test your code. And so that's exactly what we're doing. So this hanks.txt and then imdb 2010 to 12.txt are the ones that we'll be working with. But of course, we have to design the solution keeping in mind that eventually I have to run my code for that bigger file. So I shouldn't be doing things, and we'll talk more about how to figure that out, because until now we haven't talked about it, right? How to figure that out, whether like my code is good enough for larger data sets or not. All right, so let's begin. A part of it is already known to us, like how to read in the file and how to first get the data, right? So what I'm going to do is I'm going to introduce one extra module today, because we started talking about these huge data sets, which means like files with large amount of data. So why is this module important is because I want to time my code. And you must have noticed, like when using especially um, nested loops, right? You must have seen that um, sometimes your code takes longer than usual, and you must be like encountering that error many times. I don't know, not yet, but maybe from homework 6 onwards you will encounter that when your code runs forever on somebody and somebody gives you that like kill signal, which means like cannot execute your code anymore. So that means it's taking more time than it should normally. And in order to kind of find out how long is your code taking to run, we use a module that's known as like this time module. So I'm introducing it now, import time. That's it. Import time is a module, and the exact function that we use from time. And let me first demonstrate this. So I've imported that. There is this time dot time. So the dot time function will give me the number of seconds from an epoch, and you don't have to worry about that. So basically, this is like telling you the time elapsed from like January 1st, 1970, but that's not the issue, because let me show you what I mean. First, if you do time dot time and just like execute this, it's giving me like this huge number, like this is in seconds, so the amount of time elapsed from this date, 1 1970, but sorry, 1970. But the good thing is that I can, every time whenever I like execute it, let me execute it again, you see that there is a difference in some, because some time has elapsed when I executed this versus when I executed this. So I can take the difference of these two times and just tell or output how much time was elapsed between each of them. So that's exactly what I'm going to do. I'm going to create a variable called start time. And let me do that. And that's obviously going to save some like the exact time of when this will be executed. And then once I've run my entire code, I can put another variable end time and take the time.time value and then just check the elapsed time. So that is going to give me the exact amount of time that my code is taking to execute. And we can really like make our code efficient by checking that, because we know that this is like taking a lot of time. And also we can see how much time it takes for bigger files to execute, or like if you're using a lot of data, how much time is it taking to execute, and can you do something about it? So that's why we are introducing this. Right, and the rest of the code stays the same. You've seen this before, so I'm not like repeating it. Let me just copy it from the lecture notes and walk through this. All right, I see some questions. Let's take the questions first, and then I'll begin this. Just let me indent this and take the questions. MJ Alexander, your question is, will homework 5 be due the week after the exam? No, homework 5 is due this week. And the like Thursday, and I think that was announced and it's there on the homework. So no date is changing for homework 5. Homework 6 will not be released this week. Max, your question is it possible that it will run on our computers but not on Submiti? What will run on your computer and not on Submiti? If it's Python code, it will run on Submiti. Okay, so that's that. All right. So here what I'm doing is I'm reading in the name of the file, which of course is my IMDb file, and I'll start testing with the hanks.txt, right? And notice this list here. So I'm creating this empty list, which is name underscore list equals like empty. And then whatever the name of the file, right, go and read it. Notice this encoding, and if you don't put this parameter like encoding, it is by default going to take this UTF-8. And why have we included this extra parameter here? That's because you can also include some international symbols, international languages here by changing the encoding. For example, I've posted this code on the website. Let me show you here. The code that's posted on the website has this encoding ISO 88591. So this is essentially, this will also count any international language characters as well. So it's going to be able to read them in simpler terms, right? But if you don't provide that, I think like if it's the file has contents in English language, I don't think it matters. So this is optional, but if your file contains characters from other languages, then maybe it's good to just include that encoding. All right, so we know how to scan through a file for line in open that file. And then in this variable, I'm putting like the entire line, which is like the first line of this file, or maybe the first line of hanks.txt, and splitting it by this delimiter. Why are we doing that? Let's go back and see, because like every field is divided by that delimiter, the pipe delimiter, and which is why I have this dot split here, and this is going to convert it to a list. So words is essentially a list of all the elements in my list, and I just need the name of the person. So that's why I'm picking up like this words dot strip, right? And once I've done that, what is the goal of this problem? Let's go back and check what was our goal. So I have to find all persons named in the file, right? And one way to do that, and because this is like a list-based solution, until now we don't know any other data structure, we just know list. So the way I'm looking at it is like, how about we create this names list, which is this, right? Keep putting like every actor's name, which is going to be stored in my name variable, in this list, right? But also checking whether a name exists in that or not, right? Because if the name exists, then I don't want to add it because I don't want to count the same person again, right? So that's why what I'll do here is that I'll have like an if else block. So basically what I'm saying is if not name in name underscore list, which means if the name does not exist in that, then only go and add. Otherwise, don't add, right? So name list dot append name, right? Otherwise, don't add. And additionally, I'm putting like another if. This is like completely optional. This has nothing to do with the exact problem, but I just like want to output this thing to see how much time is elapsed for every like 1,000 lines processed in my IMDb file, right? So this if block is going to be optional. It's up to you whether you want to write it or not, but let me show you what I'm trying to do here. So if the length of this name list, so if this list becomes like 1,000, 2,000, right? 1,000, right, equals 0. We know this is the modulus operator. So whenever this becomes, then go and print like how much time was essentially elapsed, right? So print maybe after these many like number of observations or number of lines added, the last 1,000 took how much time, right? So the last 1,000 took this much amount of time. And maybe because I know that this, you can tell time has like these significant values. So I'm just going to have like up to 2 significant figures and these many seconds, right? So these are seconds, by the way. All right. And let me do the dot format, which we are familiar with. LEN, sorry, LEN of names. What's the name of the list? Name underscore list. I'm going to repeat it if this is like a little bit overwhelming. I'm going to repeat everything again. And then next, I want like the elapsed time. So I need some variable to get that elapsed time. Let's say I'm calling that variable end underscore time equals, again, time dot time, right? So the elapsed time here is going to be, and let me make it a little here, right? Maybe it's end time minus start time, right? End underscore time minus start underscore time. That's it. And then like once we are done with all of this, maybe we can print like how many people are there in the list. And so we can just say print number of individuals, I don't know, number of maybe unique names. And that's going to be just the length of my names list, right? So name underscore list. All right. So that's it. Let me quickly walk through what we did here, right? So first we're reading in the file, which is my IMDb, and I'm going to start with like hanks.txt, right? In that case, like hanks.txt has only 40 values. So this will not be executed, right? Whenever you're testing that, because like this will never reach this thing. And so that will not be executed, but that's fine. I just wanted to test it that it's working fine or not. And then we can start with the IMDb. So what exactly are we doing? We are checking for this name. If the name exists in the list, don't add, right? So that's why I have this. Otherwise add. So that's all that's doing here. If not name in list, then go and append. Otherwise don't append. And going back to the time module, so this time gives me the exact current time that's right now, right? So once I'll execute that here and put the output in my variable start time, right? Once I have the start time, I'm going to execute the rest of the code. And for every 1000 values, I'm putting it like into another variable, which is end time. And you can tell that the elapsed time is going to be end time minus start time. That's all this time is doing. All right. So let's execute this and see what's going on. And let me first begin with the hanks.txt. Hanks.txt. Okay, so the number of unique names is 13. Obviously, the time elapsed did not, as we like suspected, but now I've tested that my code works okay, right? So I can go ahead and work with the bigger file, which is like my IMDb 20, 10, and 12. Okay, so let me execute it again with the bigger one. And this is important, and I'll talk about that as well, why this is important. So the name of the file that I'm running is imdb underscore 2010, if I remember correctly. If this gives us an error, we can go and check. All right, look at this. There are 25,000 lines in my imdb.txt. And here we can see like for every 1000, and this I should have like created a space anyways, is taking these many seconds to process, right? And the number of seconds for every next 1000 and more 1000 is increasing in a certain way, right? By a few maybe milliseconds, and then like maybe a 1 second is added and so on. And eventually like the last 1000, they took 21.70 seconds, right? And you can get the total time elapsed by just like removing this if statement and just like getting the end time outside, right? And just check like what's the total time, which would be the sum of all these seconds here. And I'm pretty sure this is going like a minute or so, right? Or even more. So what's the point of like looking at this? Well, the first point of looking at this is that this list-based solution can be really, really slow. You can imagine for the original IMDb that has 250K values. This was just 25 or 26,000 values, and it took us like some time, right? And you can imagine like such a like bigger sized file. So this is telling us like, why is this happening? Think about the structure of my list. What am I doing in my code that's like slowing it down for every next 1000 values, right? Because it is slowing down by a little bit. It started with 17 and then went 18, 19 and went up to 21. So what's exactly happening here is that this is my list, right? When I go and do this if not name in list, initially it's fine because it doesn't have anything. So it just says, okay, go and check. This name is not there. So that's fine. It's quickly added. When I have, let's say, 100 names, right? List is a sequential data structure. And let me kind of draw it here to make things clear. So what happens exactly is that my list is something like this, right? It has a position and a value. So let's say like name 1 was added and then name 2 was added and so on. Initially, it's all fine. It just goes and checks, okay, this name exists or not. But eventually, you know that there's like name 1000 will be added, right? And when I go inside that if and just go and ask this if name 1001 exists or not, right? Right? It'll go and like this is a sequential data structure. It's going to like check each one of these, right? And so it's going to check, okay, like after scanning through all those 1000 values, no, it does not exist, and then it's going to append that, right? Or maybe it exists, so it's going to skip that and go to the next. But in either case, it has to scan these like 1000 values. And as the size of the list is growing, it has to like, I don't know, scan maybe 10,000, right? Or maybe 20,000. So every time for every single if execution, every single addition of a new name, it has to execute that like as many times because my list is growing. And that in itself is pointing to a short, I would say, drawback, like one of the first drawbacks of using list as a data structure. And that's why we are introducing something that's known as a set. Now, there is like this argument that we can improve the solution a little bit by using dot sort, because what it'll do is in that situation, we'll not be going and scanning each of these values. And let me show you what I mean. And first, let me look at the questions and then we'll move on. Kiran, your question is, can you go over the time module? Yeah, time module, the only thing that we'll be using is the dot time function in the time module. And this dot time gives me the number of seconds elapsed from 1st January 1970 until now, right? So this is what this gives me. But this is good because I can always get the elapsed time for my code, because I can first save the time that's now and then save the time that's at the end of my code execution. So that's what I'm doing here, like getting it in start time and end time, and then just subtracting them. All right, any questions about the structure of the list? This should be clear that the execution of every if statement is making me scan those values that are there in my list. And that's why the time that's elapsed is increasing with every 1000 values. All right, so a slight improvement in the solution can be achieved by not having this like names in list, but rather what I can do is just like remove all of this. Okay, this is here. And maybe I don't need the end time here. Right. And maybe just remove this print statement because we'll just like check what's the elapsed time. Okay. All I'm doing here is that I'm going to, let me think, have this name underscore list dot append name, regardless whether it is like it exists or not. So I'm going to get rid of that if statement, so I don't have to scan that 1000 or 10,000 or 20,000 size list. All right. What next should I be doing? Once I'm done with this list, I'll come out of the loop, right? Come here. And maybe also have this end time outside because I'm trying to check how much time this one takes. All right. So here I'm going to do name list dot sort. Dot sort is a more efficient way and like of sorting things because like internally it has been optimized. We'll talk about like how much time it takes and all of that in some of the later lectures. But just like remember that instead of like doing that if, dot sort is faster than that. And as I said, we'll talk about the efficiency later on. But just remember that. So all right, here when we have like sorted the list, now imagine what will I have? Because these names are repeated, so I'll have like, let's say somebody's name beginning with A first and then B and then C, but the same name will be repeated multiple times, right? So what I can do is I can go and scan through this name list and see whenever the change in the name occurs, then maybe update a counter, right? So maybe do something like count equals 1, because at least that one name exists. If it's not there, then that's an empty list. So maybe I need an if statement, but I'm leaving that to you. I'm just showing you one basic like kind of structure, what we can do here. So I'll begin, range, and then begin from 1, go up to len of name list. I'll show you why I'm beginning from 1, because what I'm trying to do is I'm going to check like every 2 elements in my list. And I'm going to check the second element first and then the previous element. So that's why I'm starting with 1. All right, so all I'm doing is scanning through that list once, and this is going to make things faster as compared to what we had earlier. Sorry, name underscore list and I minus 1. Because I'm beginning with 1, so that's fine, because I'll begin with like 1 and 0, then 2 and 1, and so on. And so if this is not equal to name list, sorry, I, right? If these are not equal within that names list, which is already sorted, whenever this change occurs, go and update this like count plus equals 1, right? And this is fine. Number of unique names, we can print elapsed time, right? So let's print elapsed time, and you can like go and execute this yourself. That you'll see this takes less time than the previous solution. End time minus start time. All right. So this is like another variation using lists, but now we have like improvised a little bit on that, because now we're using dot sort, and dot sort is known to perform better. And also like we've gotten rid of that like if statement that was going in scanning the entire list. Rather, what we're doing is like regardless of what the name is, put it there. And we know that dot sort is an efficient way of handling lists. And so I just like sorted it and then went ahead and um, just scan that list once and kept checking like the change in the elements. All right. So these were the list-based solutions, but despite all of this, we know that when the size of the list is going to grow, even here, let's say it has like 250,000 entries, this is going to become slow. And so we need something such that we can like address these issues and also be a little faster when we are dealing with bigger data sets. So that's something that's known as sets, and that's what we are introducing today. And let's move to that. I've already talked about how to test. Begin with the smaller hanks.txt, then go to like 2010 to 12 IMDb, and then go and check with the bigger one, right? Which has like 260K entries, as you can see. Okay, some of the drawbacks of the lists: very slow and large files because we need to scan through the list. We already talked about this. And so we need a faster implementation, and we do have an option for a faster implementation, which is Python sets. And so what is set? It's a new object type that we are introducing today. We haven't looked at it before. And like mathematically speaking, if you've come across sets, it's exactly the same thing in Python. So set is nothing but a collection of objects, right? And even before we jump into that, like let me show you what it means and how is it different from lists. This is an important distinction. And by the way, these braces will represent sets in Python. So let's say I have like 1, 2, 3, these elements in Python, sorry, in my set, right? And I have 1, 2, 3 in a list. Now, these are different because in sets, you don't have a position. You don't have like a position for any of these elements. So the only thing that you have is like this 1 is there or not. It doesn't have a position 0, so you cannot index. Like you cannot index here. There is no indexing. Think of these as like bag of values, like a collection of values. And now in lists, this is like element 1 at position 0, right? So that it has a position. And if there was another 1 here, right, then this one is different from this one. But in sets, you cannot have another 1. Why? Because we said that like these do not have a position, right? So this is just like a collection of objects and does not allow duplicates. So it won't allow another one because there is no distinction to make. I mean, this one exists or does not exist. It does not have a position, right? So that's the fundamental difference between lists and sets. Let's go and create a set and see what exactly do we mean and how to create sets. So, all right. So let me name like S1 equals set. So that's the keyword set. And let's create it. And let's see what S1 is. And this is just like an empty set. So obviously we need some elements to be added to this. There are multiple ways of doing it. We'll see each one of them. Let's begin by using some iterables, which means if you have a list or if you have a range function, you can convert it to a list, sorry, a set. So let's see how we can do that. Let's see maybe S2 equals, and you can use this set keyword, right? And then like maybe I have a range function because range is an iterable. And so this is like the first way of creating a set. And there are many others. So I'm like beginning with the iterable one. 0, go up to 10, and maybe jump by 2, right? And then print S2. So we'll see what this looks like. Now notice this is my set, right? So I have like these curly braces. Curly braces are for sets. And we'll see going forward, there is another data structure that has a similar like curly braces, but then there are some significant differences. So you will be able to figure out. If there are curly braces with like these elements, then it's obviously a set. Okay, as I said, it has like these bag of values, and although when we print them, they appear sorted all the time, right? I'll show you what I mean. Um, let's say I have another set S3 equals, and you can create a set like this also, like directly curly brackets, and let's say I'm putting some values, right? 0, 10, right? And then I'm going to print them, print S3, right? So this is what I mean, like they appear sorted all the time, and that kind of maybe ring a bell that they're sorted, but they're not. Again, like think of this as a collection of values. Just the output, the standard output in Python is designed such that they appear to be sorted, but it has nothing to do with their like positioning. It's just the print statement, and maybe here it's not even sorted, right? So it does some kind of a like this comes as a confusion sometimes that like maybe it's sorting by like the first element or something, but it's not. It's just like the way the set object type in Python is designed. So sometimes they appear sorted, but they are not, is what I'm trying to emphasize here. This is just like a collection of these objects. All right, a quick distinction again with the lists versus sets, and I already talked about that, but still I'm going to repeat it. Let's say I have this like list of values, so 4, 8, 4, and then of course. So this is just like demonstrating that we can have like any object types as an element in my set, right? So it could be a string type, it could be a float, maybe write it 3.2, 32, 64, 2, all right? So this is a list, right? And as I said, I can use an iterable to create a set, right? So I'm going to do that. And I'm going to create, let's say, S4 equals a set. And this is like V, because this is my list, right? And S4 got created. So if I look at len of V, it has 8 elements, and len of S4 has 6 elements. Can somebody tell me why is that? Although I created a list from that. Excellent. So Rochelle, you're right. It removes duplicates. And so that's why, yeah, Miriam, you're also right. 32 appears twice, and 4 also appears twice, right? So it just like gets rid of those repeated elements, because set can only have like unique elements, because it's just a collection of unique elements. There was a good question. Miriam, your question was, is there a way to sort a set? Yes, but you will have to convert it to a list. And we are coming to that in a short while. So like quickly, like speaking, if you use a sorted on a set, it's going to be converted to a list, and then it will be sorted. A set in itself will not be sorted. All right. So that's an introduction to sets, and as like any other Python object, these have like a set has specific methods that are applicable only to sets. Just like we've looked at lists, we have looked at strings. So similar to that, we have some methods, and because this is like this is similar to the mathematical notion of sets, the functions that apply in mathematics are also valid here. So we're going to look at them. The very first method that we're looking at is the dot add method. It's similar to the dot append, except that dot append was for lists, dot add is for sets. And we have to be like careful, and we have to remember that this dot add will not add a duplicate element. So if you were expecting to do that, if you were expecting your code to do that, then you should be using a list. All right. So how about we create some set again? Let me recreate S1 so that maybe this is easier to create. So range maybe 0 to 15. Fine. All right. So how about if I want to add like 100 to this S1, and also let's print S1 to see what it has, right? Print S1. All right, so it has all the elements until like from 0 to 14. And I want to, let's say, add 15. That's like a more logical thing. So I'll do S1 dot. And the moment you do add dot, you can see all the methods, right? So dot add 15. And well, let's see what S1 looks like. So it has this element 15, right? And let's say I do this dot add 15 again. That will be executed, but then nothing else will be added. It's not like a list where you'll have like 215s because these are only unique elements. All right. So if this is S1, how about I create another set, maybe S2, which has some other elements, and S2 equals maybe, I don't know, let me also use the range function. Set range maybe up to 6, right? So this is S2. Now there are certain, I would say, functions or certain methods that apply to two sets, and that again goes back to the mathematics behind sets. And let me like just show you a few pictures to make this clear. All right, so set is nothing but a collection of objects. So for example, this is my set S1 and this is my set S2, and there are certain like properties that are related to sets, if you remember. So for instance, if I'm talking about the difference between sets, right? So if I'm talking about S1 minus S2, basically what I'm testing is that this S1, let's say they overlap, or maybe this like some portion of S2 lies in S1. And so when I'm doing S1 minus S2, I'm saying like keep S1, but remove the elements that are also in S2, right? Or maybe if S2 completely lies inside, then I'll be removing those elements only, right? So if there were like a few elements here, like let's say 2 or 3 were overlapping, so those will be removed from S1, and the rest of the elements of S1 will be displayed. So that's like the difference. Now, if you remember the intersection, right? So if I'm talking about S1 intersect S2, and we'll see how to do that in Python, I'm interested in these elements only, right? So this is going to be my intersection. What are those elements that come up when like my S1 and S2 overlap? What are the common elements? That's my intersection. And then if I'm talking about union of these two sets, and let's say I don't know whether they overlap or they don't. If they do, right? If they do overlap, then I'm interested in all the elements. So this is going to be union. Now, an important point here is that union returns a new set, right? So if a union returns a new set, that means these elements that are in S1 and in S2 should not be counted twice. So basically, I'm going to get all the elements, and the ones that were repeated in both of them will again be counted once, because this union is returning a set, right? So that's intersection, union. I think there is symmetric difference. Okay, so that's another one. Let's say they overlap. If they don't, then obviously nothing will be returned in that case. But if they do overlap, no, so like this is symmetric. I was talking about intersection, that nothing will be returned. But in symmetric difference, what happens is that we check whatever the overlap is. And so we return the elements that are in S1 but not in the overlap, and also in S2, but not in the overlap. So think of this as like the union minus intersection. So that's what symmetric difference is. It'll just like discard these elements, right? It's going to discard these elements. So that's symmetric difference. Now, there is another like function that's like subset and superset. Okay, so what are these? So subset means if all the elements of, let's say, S2 lie in S1, there is nothing extra in S2. Like, for example, this S2 can be like, can be a part of S1 like this. Then S2 is a subset of S1, and S1 is a superset of S2. Right? Every element is included in there. There is nothing extra that S2 has. If S2 had like something like this, then it has like these elements that are lying outside S1, and so then it's not a subset. All right. So these are some of the basic definitions of these functions that we'll be using now to test these functions, and we'll also look at like how to use them in Python, right? Because we are interested in that. So let's look at that. Now I have two sets, S1 and S2. Let's look at the difference between S1 and S2. And I'll also write them down here so that we remember. So this is difference. And there are two ways of like using each of these functions. Let me show you how. So one way is to simply for difference, just like S1 minus S2. Let's see what this prints. Right, so this is returning another set of the difference between S1 minus S2. But there is another way of like using this same thing. You can do S1 dot and difference S2, and let's see what this returns. This also returns the same thing, right? So I would like ask everybody to go and like create different sets, like with different types of values, let's say with strings, with numbers, with mixed, right? And try like each of these methods and try to figure out what output is like these are going to give. I think one of the lecture exercises like makes you do that, but that's like you should be doing like additional practice in this, because um, we cannot talk about each and every case, each and every scenario. So please go back and do this yourself, because this is like really important. All right, so the second one we are looking at is intersection. Let's see what intersection does. So you can do, and remember intersection was returning the elements that overlap, that are common. Okay, so S1, if you do this AND symbol, S1 and S2, this is going to give you the common elements. And there is another way of doing it, which is S1 dot, and here you can see this intersection S2, right? So again, the same thing, but yeah, this is intersection. The third one was union, and let's see. Again, two ways of using union operator. One is like do S1 and use this pipe delimiter that we've been using until now in the txt files. We've seen that, I mean. So this is the union operator, this pipe delimiter, right? Let me show you, right? So all the elements, but obviously because this is also a set, so nothing will be repeated, which is fine. Again, similar to what we did earlier, do a dot and you can still get union, and that's that. Again, the same thing. The other thing that we talked about was symmetric difference, right? Symmetric difference. Again, two ways of doing it, similar to what we said. Symmetric difference will have values in either S1 or S2, but not in both, right? So it just discards the overlap. All right. So again, one way of doing it is to use this thing. Where is it gone? This symbol here, I don't know what to call it, but this symbol will give you the symmetric difference. And so these, I know that these are the common elements. Maybe we should have added like something else here as well. Let me make it more interesting. S2 and then S1 and S2. Yeah, now it has like those removed, the common ones removed. All right, again, similar to that, you can have S1 dot symmetric difference, S2, right? And this should give you the same, obviously. And then there is this is subset and is superset. And like these two methods are different in the sense that they return a true or a false. They don't return like what is the superset or what is the subset, right? So obviously, because it's either a subset or not. So for example, if I'm saying S1 dot is subset S2, right? S1 dot is, oops, okay, subset and superset, right? So if I'm saying S1 dot is subset, let's do the subset first. S1 dot is subset S2. This is saying these are like, are all elements of S1 also in S2? Is that true or not, right? So if we execute this, right, this should return a false because my S1, remember, is like the bigger one. So obviously not all elements of S1 are in S2. So is S2 basically this is true or false, right? Another way of writing the same thing is S1 less than equal to S2. If you're doing that and both are like sets, then this is what this means, right? Whether like all the elements of S1 are also in S2. Similar to that, we can use like something that's known as a superset, which is S1 dot is superset, this one, S2. Are all elements of S2 also in S1, right? Just like flipped. Again, the like sorry, I mean, this returns a true or a false. So are all elements of S2 also in S1? Yes, this is going to return a true. If all of the elements, if there is a single element that's extra, then this is going to return a false, right? Or another way of writing it is S1 greater than equal to S2. Similar to what we did here, right? So this is subset and this is superset. All right, let me quickly go back and see if I missed any of the methods that we checked. Okay, dot clear. I think I forgot this one. And again, this is pretty like, this should be clear. What this dot clear does is that, let's say I have like S1 dot clear. It's going to remove all the elements in my S1. So that's going to be like an empty set now. So S1 is an empty set. That's all this dot clear does. I think apart from that, we did dot add, we did clear, difference, intersection, union, is subset, is superset, symmetric difference. All right, I think we covered all of them. Let me take the questions and then we have to go back to the IMDb problem again. All right, lots of questions. Let me scroll up. Sion, your question is, can you modify sets like a list? I'm not sure what exactly do you mean by modify, because there is no element positioning there, right? So if you're talking about like updating a particular index like in a list, I'm not sure if you want to do that in a set, because how can you do that? There is no position. You just go ahead and do a dot add. So if that element is not there, it will be added. If it's there, it won't be added, right? Caesar, your question is, so like in a list, the value will be retained without having to be sorted in a new variable. Okay, so that's the concept of like Python dynamic typing, right? But I'm not sure what you mean by value will be retained. I mean, if you're updating the same set again and again, then yes, it is the same set that's being updated. But if you're applying these operations, like here, this is creating a new set. For example, this union is creating a new set, intersection is creating a new set. And you can definitely go ahead and like do something with that set, like maybe save it in a variable or something, right? So most of these operations create a new set, except of course subset and superset, because they are just like Boolean output, but rest of them are creating new sets. Miriam, your question is, how would we find the union or symmetric difference with 3 sets? Well, it depends on what exactly you're looking at, right? Think of the Venn diagram that I just showed you. So if you're looking at the symmetric difference of 3 sets, like go and find the symmetric difference of the first 2 and then do the symmetric difference with the third one. It's always best if you're working with more than 2 sets to go and draw the Venn diagram, because then you can like create your expressions, and the expression will depend on like what exactly do you want. For example, here, this is like a quick example. This one is returning a set that has the symmetric difference of S1 and S2. Maybe you can try doing a dot symmetric difference on this set, right? Or maybe use like parentheses to find the output of one of them and then do a symmetric difference on the third one. So expressions will be similar to what we've done before. You will have to figure out like what exactly do you want. Gianni, I'm not sure if that's how we pronounce your name. Can you also use S1 in S2? I'm not sure what that question means. But if you're talking about whether like S1 is in S2 or not, like if all the elements are in S1 or S2 or not, I haven't personally used that ever with sets. You can try doing that, but we have like such nice methods there, so why will we do that? But for an element, you can do that. What I mean by that is like you can do things like 1 in S1. That you can do. If 1 in S1 or 2 in S2, that you can do. Okay, Caesar, your question is, can you explain clear again? Well, dot clear just like clears the set of all the elements. So S1 dot clear means just remove all the elements and return an empty set. Miriam, can we use dot find and dot remove in a set? Well, that's a very fundamental question about Python. And I think I've repeated that so many times. Whenever we are working with a Python object type, You cannot just go and assume that the methods that we're working with lists and strings will work here. So dot find is a string method, and dot remove is, I think, a list method, right? So the best way out is to do an S1 dot and see whether that method exists or not. I'm pretty sure it won't exist here because it's like specific to that. So just go and check these methods. And also, like in terms of dot find, logically speaking, you cannot have dot find in sets. Like what will dot find? Finds the index, right? And so there is no index in set. So logically speaking, I don't see that we'll be able to do that. Regarding dot remove, there is another method that we use for removing from sets, which we'll see, I think, when we begin with dictionaries, because we have like a similar sort of method for sets. So we'll see that later. Um, yeah, so dot find is like logically not correct. Caesar, yeah, so we'll come to dot remove, or sorry, dot pop and dot remove as I answered Miriam as well. So we'll talk about how to remove elements. Um, Rochelle, your question is dot clear the only function from these that would work on lists too? I'm not sure if dot clear was ever used on lists. I don't remember using a dot clear on list. Can we use that? I haven't personally used it. So that's a good one. Yeah, so maybe yes. And we will see a lot of overlap with methods with dictionaries and sets. So that's another thing. Very few overlaps with lists. And as I said, like about the dot find, you should always be thinking about whether that method makes sense for this object type or not, right? Okay, all those very good questions. Gianni, I think I already answered that question. Lauren, your question is, could you explain the difference between superset and subset? Yes. So here, when I'm saying S1 dot is subset S2, the question that I'm asking is, are all elements of S1 also in S2, right? And so that's like whether this is a subset of this or not. When I'm using superset, the question I'm asking is, are all elements of S2 also in S1? That's all, right? And think of this in terms of like the Venn diagram. Are all the elements like, will that circle lie within the outer circle or not? Okay, so I see all those are very good questions. And by the way, the question about dot clear was really good because I think I never used with lists dot clear. So that's an excellent question. And yeah, I mean, generally speaking about methods, just like go and do a dot or do a help. That's also another one, help sets, or do a help S1. This is going to give you all the methods that work on sets, right? But for now, I think we are good with like dot add and these methods. I think all the problems that we are looking at right now should be like solvable, I would say, with these methods. So I don't think we need any new ones. But yeah, please keep asking more questions. But let's move on to the basic issue that we were facing when we looked at the list-based solution, right? And yeah, we will explore this as well, explore like why have we introduced sets? Think about like S1 to be the set of actors in comedies, S2 be the set of actors in action movies, right? And how useful these operations can be. Like who are the actors who are only in comedies and not in action movies? Or who are the actors that are in both? Or list of all the actors who are in comedies and action movies, right? Or list of all the actors who are in one of like either one of them but not in both. So all these questions can be answered by these operators or these functions. All right. So I think I already did a demo of all these examples. So let's move on. Yeah, we talked about all of these, right? How these will work. And of course, going in and checking with different inputs will make things even like clear to everyone. So as I said, back to our problem and why is this important? Well, the first thing that you should know about sets is that they are faster. And we will talk about like why they're faster, but for now, it's okay to remember that we can, internally there is a method called hashing on which like sets are based. And hashing is like a faster way of accessing elements in any data structure. So that's like number one. And because this is like set-based solutions are faster, and I think in homework 6, you'll be asked to implement a set-based solution on larger files. If in that problem, you go ahead and implement a list-based solution, it's going to slow down so much that you are going to get that kill signal error on submitting, right? So why are these faster? We'll talk about that, of course, in a short time. But let's look at the solution itself, right? How can we use sets to solve this problem of getting the unique names of all the individuals in my IMDb file? And by now it should be clear to you because you can tell that a set holds these unique names. So the good thing about sets is that I'll just go and do a dot add, right? I don't have to do like any kind of an if or even like this thing here, remember, right? Even in a dot sort based solution, I had to like scan through the list again. So I don't have to do that in a set based solution. So let's look at that. And the input is going to be similar. Like let's have all of this here. All of this is required. And additionally, I'll have like the time elapsed thing as well, right? So this part will also be there. And let's see how simple this can be. That's all. And instead of like names list, right, I have like, let's call this names, and this is a set, right? Everything stays the same. This is a set, and name is this, names dot add name. Keep adding names to the set, and the fact that sets are going to allow only unique names will take care of like the number of unique names, right? And the number of unique names is length of this set. All right. So let's look at like, let's execute this code and see like how much time this takes. And I'm going to like run it not on the Hanks file, but on the main IMDb 2010-2012, because we have seen for every 1000 um, observations, my list-based solution was taking a lot of time, right? So let's try doing that. Okay, so the name of the file was imdb underscore 2010 12.txt. All right, and I should have done like rounded it to up to 2 decimal places, but that's fine. Just look at the elapsed time. It like scanned through that in just 12.0 some seconds. I don't know, even less than that, right? So the thing is, if you remember, if you go back and like look at this one, right? Every 1000 was taking like 17 plus, or I would say 18 plus seconds. And this like the entire 26,000 values just took like what, 12, right? So there is this like huge difference in the amount of time this solution takes. And in fact, even this like sorted one is going to take way more than this one. And you can go and test that. But like, what's the thing that's making it so fast? That's the question here, right? So first of all, as I said, there is this basic structure in sets, and we'll see more of that in dictionaries, that uses the idea of hash maps. And these we don't have to jump into that in this course. So it's outside the scope of this course. And of course, if you're taking data structures after this, you will know more about it. But these hash maps are faster way to access values because they don't have this sequential thing like lists, right? So there is no sequence that's saved in my data structure. It's just these bag of values, and you access them using keys. And we'll see again in dictionaries what these keys mean. But there is some math behind it. There is some theoretical comparison behind it. And let me show you that. Uh, Okay. We already looked at the sorted thing, but I think that question came up earlier. So let me, before jumping into the math behind it, also show you that if we do something like this, and let me again create this S1, let's say this is a set 10 minus 1. This will be useful going forward. So that's why I'm showing you again. And the lecture notes also talk about it. So if you have a set, let's say this, right? And if you use a sorted on this S1, right? Definitely you can use sorted on a set, first of all. And this is by default going to convert it to a list. I think that question came up earlier, but let me show you. I forgot to demonstrate. So this is going to return a list. Of course, we can sort values in a set, but you'll have to use sorted, and the return value is not going to be a set anymore, right? Because there is no notion of sorting in a set because it just has these values. All right. So that's that. talking about the speed, you can tell that the set-based solution is, I mean, way more efficient than my list-based solution. And that also kind of points you to using sets more often than you've been using, then you use lists. Of course, for some problems, it's not possible to use sets because then you need the positioning of the elements. But whenever you don't need them, for example, in this solution, in this problem, just go ahead and use sets because you can see how efficient these are. Okay. So going back to comparison of the running times for our two solutions. This is the important, I think, key takeaway of today's lecture, which is like in the list-based solution, what was happening? We saw that every time a name is added, whenever we are doing that if check, right, it would scan through the entire list to decide if it's there or not. And then the work we are doing in order to scan that is proportional to the size of my list, right? The bigger the list, the more work I need to do to scan and find out if that name exists or not, right? And so that means although we have this time, the exact time that we are getting from this module time, right? But as I said, there is a theoretical notion of time, which is related to the amount of work that you're putting into your algorithm in comparison to the size of the input. Okay, what does that mean? Well, let me show you in a picture here. Okay, so in my list-based solution, right, if my n is 10, n by n I mean the size of my list, the maximum size of the list or the size of my data. And so for example, here my file size, right? Let's say my file size is 10, and the worst case that this can go to is like my file will have like 10 values, right? And so the size of my list in which I'm going and doing my if will be like 10 values, right? Max it's going to go until 10. Okay. So now if my n is 100, right? So then obviously the size of my list will be like 100. And so the amount of effort that I'm putting in is somehow, I would say, proportional to the size of my n, right? The bigger the n, the more the work I have to put in this list-based solution. Okay. So then when we are like expressing our effort in terms of the size of the input, there is something that's known as the big O notation. You don't have to know a lot about it, a little bit about it. And what this tells us is that whenever I write a big O, this is an uppercase O, and then like the size of the input, it could be anything. Like this is the convention in math, right? To write the big O notation like this, like a bigger O, and like how much your algorithm, like what is the order of the operations that your algorithm is taking, right? In our case here, the order of operations, the worst case order is going to be of the order n because my effort is directly proportional to n. Okay, how is this important? That's important. Let's say you're scanning through the list for some, I don't know, pair of values, let's say, and you know whenever you're doing a pair of values, you need like for I in some iterable, I don't know, some list, like, right? And then you need for j, like this is a nested loop in list again, right? This is the usual structure. Okay, if the size of this list, and again, the variable that we use throughout is n, we always, like that's the convention, we use n, right? And so what's happening here is that for every n, we also go and scan this n again in a nested loop, right? So in a situation like this, in a solution like this, for any problem, like in general, my effort is usually proportional to n squared, right? Because I'm like scanning the list twice. For every element in n, I'm scanning the entire list again and again and again, right? So my effort is directly proportional to n squared, which means like this algorithm here is of the order n squared. So this is how we express like theoretically. And this is usually the worst case because maybe like you can say, if you really go into the details, you can say, okay, I didn't even pick up the rest of the elements, but that's fine. This is like the worst case complexity, right? So think of this as like the worst case that can happen, right? Even in our like list-based solution, you can tell that like maybe I didn't even scan through the entire list and maybe, you know, I just stopped at some place because of this. That's fine, but we are expressing it in terms of the worst case complexity. So this is like how we theoretically denote how bad or how good my algorithm is in terms of my input size, and that input size is n. All right, so why is this discussion important? This discussion is important because we did this time comparison, right? If you go and run, let's say, this code here on your computers, there might be some difference in the time that you're getting in terms of the seconds versus what I'm getting. Why? Because this is also not just based on like what kind of a solution I wrote, but also like what system you're running your code on, what computers are you using, when were you running, right? And all of those things. And so this time can get impacted by that, right? But this theoretical notion of like big O, this big O notation, is not getting impacted by any system. Like no matter wherever you're running this code, no matter what you're doing, but I have a way to compare algorithms in some theoretical way, right? Let's say you're running code on your computer and your computer is faster than mine, right? And so there can be a variation in time, but we like as people in computer science, we needed some way to compare an algorithm across, like throughout, right? Theoretically. So how can I say that my code is better than yours or your code is better than mine? Well, I have this theoretical way of comparing them. And this is like a huge subject. We're not even going into like any further details as of now. Just remember that this is a theoretical way of comparing solutions. And like, why is this important right now? Because I want to compare my list-based solution with my set-based solution. All right. And as I said, this will be covered more in data structures if you're interested. For now, it's enough to know, like if you can just express the effort in terms of the size of the input, that's enough for you. If you can just like look at the input, oops, I think my computer is going out of charge. Okay. Yeah. All right. So why is this important? As I said, we saw that our list-based solution is like of the order n. We just saw that like order n. And what is it about my set-based solution? Why is it so fast? And then you can say that maybe my computer is better than yours, and so all of those variables are there. But then we have a way to theoretically compare these two algorithms. So let's do that, right? So internally, Python is using this technique called hashing. Hashing is nothing but like things are stored in a way that like a key is pointing to your value. And as we said, think of like high level as a bag of values, right? These are a bag of values. So the moment you go in and try to find some, like you do a dot add, let's say, right? We were doing a dot add in my set. Okay. So what does this dot add do? This dot add, unlike my dot append or unlike my if, it's going to go and check the set. Dot add is going to go and check the set. And the way it checks is by using this hashing, which means it's going to jump to a key and see whether it's there or not, right? And it doesn't have to scan every element because there is no sequential storing of elements. Either that key exists or that key does not exist, right? And so the good thing about like hashing is that it's an order one operation. And why is this good? Because you're not scanning regardless of what your input is. If my n is like, let's say 100,000, my effort is not dependent on that. So I somehow got rid of the dependence of the effort on my input size, which I cannot get rid of in my list-based solution. My list, the effort is dependent on the size of my input. And so that kind of explains, right? It's independent of the size of the set. So that kind of explains why it doesn't really matter. Of course, it's going to go a little bit like slower when there is a huge data set, but not as much. You will see. Why? Because I have this bag of values. Of course, the bag has grown. And so when I'm going to go and check whether that key exists or not, this will take some amount of time, but it doesn't really impact my efficiency, no matter what the size of my n becomes. And so that's the idea. That's the fundamental idea behind, like theoretically speaking, why my list-based solution is so slow and why my set-based solution is so fast. And like you will see a full implementation of this hashing in dictionaries. Dictionaries are the most generic sort of, I would say, representation of hashing, and sets can be considered as one special case of dictionaries. We'll see that, but for now, it's enough to know that like um, this is an important data structure in the sense that this is the first one that we are seeing that uses hashing. It doesn't have an element positioning. and that makes it so much efficient, right? All right. So, and yeah, and another thing that I wanted to add to this is that we have that dot sort based solution. And if we run it, we will see that it works better than my original list based solution. And that's because this Python sort is like more efficient internally, and it's like of the order log n, which is not the case with my list. So it makes it like slightly faster and slightly better. So that's all. We'll talk more about like this order n, like how to compare different algorithms, how to like looking at the code, can you tell the theoretical efficiency of that and on. But in later lectures. For now, it's enough to know that there is some effort that you're putting into your solution, and how is that effort related to your input. All right. And this also goes back, like generally speaking, whenever you see that your code is taking more time, right? Like there are a few pointers here. So the thing to do is like, of course, time it, go and do this, like use this time module as much as you want, right? Also, like generally speaking, look at like, do you have a nested loop? And is the input like the size of the input or the like the lists that you're working with or anything that you're working with, how bad can it get, right? That should like somehow tell you that like maybe something is going wrong there, which is why my code is so slow, right? And obviously like always time your code. That's a good practice to know how much time it's taking on your computer. But then you can always tell why and where, like whenever there is a loop and you have an if condition, you should know that this is the place where it's kind of slowing down, and this is where I need to do something to get like rid of that. All right. So that's about the efficiency. As I said, we'll discuss this type of analysis more. So whenever you see big O notation, right, this order n, this is how we read it, order n or order n squared, right? Or order of n squared. Well, I'm used to saying order n squared all the time. So it's the same thing, but we'll talk about it more when we talk about like algorithms, especially when we look at searching and sorting. All right. So that's that. In like summary, I would say Python largely hides the detail of the containers. We haven't like seen this kind of analysis before. We were very happy using lists, but now we figured that this is like a container, and every container has these properties that are associated with it. For example, for lists, we had like this sequence of the sequential access, which was until now really good, right? If you think about it, was really good. But now we saw there is a separate set of problems that can create issues when we're using this kind of container. And so sets come in and they like rescue us from there, right? And like generally it's hard to know which is more efficient and why, but now we have some idea, right? Of course we have some idea of like why sets are more efficient. As I said earlier, for programs applied to small problems, including small data, efficiency doesn't matter, right? If I'm running this code for the hangs file, right, it would like hardly take any time even with the list, because there are just like 40 values there. But it matters when my size of my file has become like 25,000 or 26,000 and it's going to go to 260K. So that's when efficiency matters. And that's why we never talked about it until now, right? And for longer programs and programs that work on larger data sets, efficiency matters a lot. You'll see sometimes tremendously. In fact, so much so that this is like one of the important points of like when comparing your code with any other. This is like one of the most important things that you will see, and sometimes your code is not considered like as correct because it's failing on a larger data set. So keep that in mind as going forward. Good thing with Python is that my container, like my choice of my container, is internally doing certain things to make my code efficient. That's the power of Python, which is not true for other languages, and you have to optimize your code yourself, right? So all you have to do in Python is to generally know which data structure is internally doing what, and that's enough. All right. So today, in summary, we looked at sets. Sets are like, they realize the notion of a mathematical set. And we looked at we know that sets are faster. And in addition to that, please pay attention to the operations or the functions or the methods that we used with sets, because they are really, really useful for solving a lot of problems. All right, so that's it from my end for today. I think we ended the lecture 5 minutes earlier. You should go ahead and do this extra practice, but I think we've looked at these. And this is like asking you to write the function of a union and intersection symmetric difference yourself. So that's something that's doable. That's it from my end. Thank you so much for joining. And if you don't have any questions, you can leave. Thank you. Yeah, thank you, Rochelle. Thank you, Danielle. Okay, let me look at the code. Where exactly are you getting the error? Imdb file encoding. Yeah, the dot strip is missing the parentheses, right? Where you like reading the input. Yeah.